folks who are not able to listen in this time zone. So I was using my time quite efficiently. I use my time, whatever I can do. So I was trying to learn something from YouTube. Uh, I learned a lot actually from YouTube, quite a lot of things. So, so it was productive time, not like I won't call it unproductive, but I could not teach. That was a Monday class I had to cancel. So tomorrow I have a lecture, and Friday we have another very important lecture by a company. So that will be taken over, and then Saturday I'm going to teach Akka. So Saturday we'll do some hands-on. For hands-on, actually, I need to look at Windows PC because Mac doesn't allow those softwares. So I'll share the folder today with you. So you will be able to install it in your computer, that software, and I'll share some example files. So preferably you would like to sit with your laptop rather than mobile phones. So let me start this lecture, understanding the lateral and vertical resolution in an atomic force microscope. So it is quite important topic, and it's quite complex as we learned in other microscopes also, like transmission electron microscope and scanning electron microscope, and allied technique, for example, chemical mapping in transmission electron microscope. So here, even temperature plays a role. So there is one. I mean, so when you say resolution, basically resolution is understood as the concept is taken from just a moment. Somebody is trying to. Yeah, don't use your annotation. Yeah. So. So one is called force resolution actually. How much, because we are using atomic force microscopy, so there are two purposes of atomic force microscopy. Prime purposes, there are many other purposes, that I would like to know the resolution of dimensions of measurement on a surface, right? Lateral resolution as well as vertical resolution. So please note that here we have two terms for spatial resolution, lateral as well as vertical resolution. We didn't use these two terms for separately for transmission electron microscope because there is no vertical resolution, there is no depth sensitivity there. So only we had two-dimensional projection of three-dimensional objects. So as I mentioned earlier, this is the major advantage of atomic force microscopy, that you get true three-dimensional resolution. Second resolution I would like to teach you today is the force resolution. What is the force sensitivity of cantilever? How small, for example, I wish to measure 1 piconewton, for example, covalent bond between two molecules which might be forming. So I can put one molecule on tape and another molecule on the substrate, and I would like to see what is the force between them, whether it is a covalent bond or some other bond, what kind of bond it can form. So I would like to calculate the bond energy. So is it possible can I do that? Can I calculate the bond energy? Can I look at the adhesion, all kinds of things? So then this obvious question comes: what is the sensitivity? How sensitive I am to this kind of force measurement, and what is the resolution? How small force can be measured? So today these two questions we'll look at in detail, and finally we will reach to some conclusion that why ultra high vacuum is better for frequency modulation AFMs, which are gaining more and more popularity, though these kinds of AFM are more expensive, but nobody can deny that you can reach true molecular resolution. For example, you can look at the benzene ring, as I showed some examples in the previous lecture. So this is quite interesting topic. Let's see one by one. So let us understand lateral resolution. So AFM is a computer-controlled local probe technique, which makes it difficult to give a straightforward definition of AFM resolution. So this computer control stuff we'll note later on. Maybe Saturday I'm going to teach how computer can. Me mute all of you. Yeah. So lateral resolution is largely limited by the geometry of the tip. All of us know that sharper tip gives you high resolution. It depends upon geometry of the tip as well as on the surface roughness, both. So surface, what do we mean by surface roughness? That is the topic of Saturday when I teach you the image analysis. So, and vertical resolution is limited by thermal noise. Now, what is the thermal noise? Let me show you a little bit by this new tool. Let me see if I can manage it. So, thermal noise is essentially, I'm not very good with that because I got it today morning around 8 o'clock. So I was excited as a kid to see that, and I brought it to the office because I could not wait to show it off to you. I wanted to show it off, right? So this is my tip, which is not doesn't look like a tip, cantilever, and this is AFM tip, right? Wow, so nice. See, it is going in another direction, right? You can see that it's not fine. So, so this cantilever can move in this direction, right? It is, suppose you let it resonate in air. So when it is free, so this cantilever will move up and down because of the thermal noise, kBt. This is written here, kBt. And K is the spring constant. So if this cantilever, this material, if this one, sorry, this is silicon or silicon nitride. If it is thicker, so then this movement, free vibration is going to be lesser and lesser, right? So this is a free vibration or oscillation of the cantilever. This can't be avoided. This is because of this temperature factor, this temperature factor, right? This one. So, and this is spring constant, right? Now, if you increase this spring constant, right? So what will happen that this delta Z will decrease because this has become stiff. So free oscillation is less. This basically limits the Z resolution because more it is more vibrations up and down, more larger is the amplitude of this tip. So you can't have, so lesser becomes your confidence in measuring the Z dimension, right? So basically you want to measure Z dimension. So if it is already moving up and down so much, so then obviously your confidence in measuring this height will be less. I hope you understand this. So you would like to reduce this. You can reduce this by increasing the spring constant, and spring constant can be increased by making this cantilever stiffer, or by decreasing the temperature. Finally, it is thermal activation energy which is making this resonate. So if you consider room temperature, which is written here, right? It's a European room temperature, not my room temperature, but it has become standard. So thermal noise, if you calculate, if you put this number here, T here, and then so for if you take K as 1 Newton per meter, which is typical amount for spring constant. So if you put this, then you come to this is your vertical resolution, which is very much achievable. So it's almost a fraction of angstrom. Okay, let's say 1 angstrom or maybe. So this can be better than this. Actually, some manufacturers can reach to 0.1 angstrom rather than 0.74 angstrom. So if you reduce temperature, you can make it better. Or if you take stiffer cantilever, so you can get better vertical resolution. So if you compare this amount with, for example, thickness of graphene, okay. So now you can see that in comparison, for example, thickness of diameter of hydrogen atom is 1 angstrom. So I think it is very good. So if you would like to measure thickness of diameter of hydrogen atom, so if you can measure it by 1 angstrom plus minus 0.1 angstrom, then you're happy with that. So, so this is the power of this AFM, that this can be, this is unbeatable actually. And you can't get it in electron microscopy, and you get the true images in AFM. Okay, so let's go to the next. How do I go? So lateral resolution of AFM. How can yeah? So now we can now we have the vertical resolution. So we can calculate the lateral resolution, because lateral resolution is determined by vertical resolution also. Let us look at this, how they are connected. So this is our tip. If you can see this, this is our tip. Oh, sorry. You may see this kind of disturbances because I'm getting used to. Okay, so this is our tip, and this is tip radius of radius of curvature R, and these are our rough features, right? So you can see that this is one grain and another grain, which are sort of convoluted. So our resolution is whether we can distinguish between this peak and this peak. So our resolution is D here, okay, this distance. If we can resolve these two features, distinguish between these two features, then we will say that yes, these two peaks are resolvable. Now this lateral resolution D depends upon R because of convolution effects. Also, the height difference between this feature as well as this feature, which is delta H. And this is our vertical resolution, delta Z. So this depends upon R. Fine. We already know that tip, smaller the radius of curvature of the tip, better will be the lateral resolution. So this is already factored in. Delta Z, which is vertical resolution, is quite important here, as well as this amount of roughness. This is basically amount of roughness. Delta H is nothing but amount of roughness. So larger the roughness, you can say that your D becomes probably larger. Yes. So if we put this some of the numbers here, so we can calculate that. Suppose we put delta Z of 0.02, which is our vertical resolution, around 0.2 angstrom, which is fine. So now we can calculate the value of D in nanometer. So for example, let us not take these values because these are quite small. Let us take 10 nanometer. 10 nanometer is quite practical, or 5 nanometer, because see these values this one, and I'm sorry, I have to select NO2. Yeah. So if you see that this value is practical value. Actually, most of the AFM tips, the radius of curvature is around 10 or less than 10. I mean, okay, either you can select this or this. These are ultra sharp probes. Normally, these are expensive, and more than 10, nobody uses. Actually, these are actually worse quality tips. Usually, 10 nanometer radius of curvature probes are those probes where you need to coat certain layer. For example, you want to coat a magnetic layer on the tips, then the radius of curvature may go up to 20 or sometimes 50. For example, you want to coat gold layer, metallic layer. So for example, you want to do some chemistry or biochemistry or typical some catalytic chemistry, and you want to look at for example, your tip can also work as a catalytic surface. So you can design the segment. So if you see that if your delta H is 0, so you can see that delta H is typically, if you, it depends upon your okay, so features. So your D value will become roughly in few nanometers, which is not bad actually. Okay, you can improve this further. For example, this will be ideal choice that for 5 nanometer, 1 or 2 nanometer is not bad actually. So you have these guidelines, and you can improve these parameters. But as I have been mentioning, that one should bear in mind that simple geometrical model which we are using does not take into account the deformation of tip and sample, which I've been always mentioning. I gave the example of your palm, and if you just take your finger and try to press your palm, then you will notice that the back side of the palm and the basically different areas show you different kinds of deformation. For polymeric sample, it becomes more serious, this deformation, and there this simple model may not be true, okay, because contact area undergo tremendous change. Now, let us go to the next one. Yeah. So, due to the finite sharpness of the AFM tip, the apparent width of the surface feature is larger than the real width. This is the so-called convolution effect, which must be considered for correct interpreting AFM image. I would like to tell you one more thing, which is not there in the slide. Let me draw certain things actually. So normally we consider tip to be like this, okay, but generally tip is like it may have this asperities, okay. So sometimes what happens that if you zoom these areas, so this tip, it's not exactly spherical. This may have some features like this. So you end up using one of the asperities in imaging. So actual tip curvature, for example, if you further zoom it. So what about this tip? So your radius of curvature, for example, you say that my radius of curvature is 5 nanometer. So, but 5 nanometer is the radius of curvature of entire probe. For example, the radius of curvature is for the entire probe. But about this, this one, this one. So this one is much smaller than 5 nanometer. Okay, it's maybe 1 nanometer. So normally this question is asked that, okay, your radius of curvature is 10 nanometer or 5 nanometer. How can you get sometimes atomic resolution or subatomic resolution? So answer lies this. So that's the reason that you must examine this part of the tip very carefully under scanning electron microscope. So then you know the actual tip geometry, and you will be able to put it in the geometric model for further calculation. how does AFM resolution depends upon the quality factor of the AFM tip? This is the last topic and quite interesting as well. So as we learn that quality factor, let me explain you what is quality factor. So let us first draw the AFM probe. So AFM probe is essentially something like this, and this is moving up and down, right? Okay, because of the temperature kBT. Okay, fine. So now, if you, this is called its resonance frequency, F0, free resonance frequency, free, okay, there's one free amplitude and free frequency. If you plot it here, so it will, this peak will look more like a Gaussian peak. Okay, so this is the, we choose a certain, so this is your F0. This is frequency axis and this is amplitude axis. Okay, I have not drawn this, but so and this is called the FWHM, right? Full width half maximum at half maximum. FWHM. Now, ideally, ideally you would like to keep this peak width as small as possible. So that is called the quality factor. Quality factor is the ratio. Quality factor, as the name suggests, is represent the quality of the probe. So smaller the FWHM, the better the quality factor is. Quality factor also depends upon the environment. Suppose, because if you are moving this tip in air, so air will apply its own drag, right? Suppose there is no air molecule, so this quality factor will be different. Then you can see from your day-to-day experiences, right? If you take any oscillator and if you move it in water, the frequency or amplitude will be different. Sorry, amplitude will be different, and then if you move it in air, you can't do the experiment so easily in vacuum. But at least you can do this thought experiment actually. I love to do thought experiment when I don't have this access to actual experiment, right? So it's a good practice. So now if we look at this, we get the force resolution. If you remember, I promised you that I will show you the force resolution, how small force you can measure. So AFM resolution is dependent on the quality factor of the cantilever, which is a measure of energy loss of the oscillation. So quality factor is defined a ratio between resonance frequency divided by delta F, and delta F is frequency change, as we have learned already. So typically, if the resonance frequency is of the order of 300 kilohertz, so quality factor Q can be around 100. So that means, so larger this value, so larger this value means smaller this value, right? So if the delta F is smaller, so Q will go up. Fine. So for bad quality tips, so delta F will be larger and Q will be smaller. So Q in ultra high vacuum is approximately 500 times that of Q in air. Since Q is much larger, that means sensitivity of AFM can be an order of magnitude higher than in UHV than in air. That's why AFM is recommended in ultra high vacuum chamber, because sensitivity goes up. But here is a catch, that so now question arises that why don't we buy AFM with UHV system all the time? Because it is not needed for amplitude modulation AFM. If you remember that I showed you that this dynamic modes have got there are two types of dynamic modes: amplitude modulation as well as frequency modulation. Frequency modulation uh, is suitable for ultra high vacuum. We have already discussed that. But if you use the normal AFM, which we call it tapping mode AFM, where we look at the amplitude change, so amplitude sensitivity decreases if you do this in UHV. So that's why it is not recommended to do the so time scale of the amplitude change is linearly dependent upon Q in the amplitude mode. So that's the reason that you would not like to do the normal AFM in tapping mode AFM. I'm using, when I say normal AFM, just please note that it is amplitude mode, okay? Because people are more familiar with the amplitude mode. People hardly use frequency mode. But for if you want to use frequency modulated AFM, then it doesn't matter because it doesn't depend upon the quality factor here. So you can just use it without any problem. Of course, ultra high vacuum has got an added advantage that the water layer. Please remember that capillary forces are absent. So that is an advantage in the ultra high vacuum systems. So that's why most of the purists, they love to do for highest resolution, they love to do measurements in the frequency modulated dynamic AFM in ultra high vacuum. So that is the best combination. If you ask me, how can I achieve the best AFM resolution? And another thing that, as you have noted, that tips should be stiff. Stiffer tip leads to better vertical resolution. Tips should be super sharp. That leads to higher lateral resolution, and surfaces should be smooth. So you get much better lateral resolution. And there should not be any adhesive forces between tip and sample. Adhesive forces can also limit your resolution. So these are some precautions which you would like to, practice if you, anytime you do AFM on your sample in future. So this lecture is not just for your PhD career. It will help you throughout your life. You become faculty member or you become scientist in the industry. Okay. So because these machines are becoming more and more readily available. So I think this is the last slide, and then we'll take up the questions. So these machines are becoming more and more available in industries, in academics. One of my own students, Chandrasekhar Saran, he spent a lot of time with AFM, and he's very good with machines, though he's from biology background. He was interested in making a career using atomic force microscopy and industry. And of course, he was trained in electron microscopy, analysis, and other details, because through these lectures only, whatever information I have given to you. So he was more than any. I mean, his interest level was more than anybody else. So he got immediate opportunity after PhD in industry in Dr. Reddy's laboratory. And I think last week he called me, and he's happy and he's well settled. So what I'm trying to tell you is that if you learn any analytical chemistry tool, so there are not many people in academics and in industry who are very good with these machines, and this skill is just going down. In fact, in my own group, I have seen that over the period of time, hardly a handful of students were really interested in doing hands-on training on AFM, and out of that, only a few turned out to be really good that I could recommend them for serious handling, serious things actually. So these things are not easy, I understand. and it takes time, you should have a flavor for, you should have a taste for, like people say that one should have taste for teaching. Similarly, for handling instrument, making instrument, one should be interested. Then only things starts working in your favor. Otherwise, nobody can help if the interest is not there.